For over 2 decades, scientists believed they had figured out one of the most fundamental aspects of our universe. Dark energy, the mysterious force pushing galaxies apart at an ever-increasing rate, was thought to be constant and unchanging throughout all of cosmic history. This force, which makes up roughly 68% of everything in existence, seemed to be a fixed property of space itself. But in 2024 and 2025, data from one of the most sophisticated astronomical instruments ever built began telling a different story. The Dark Energy Spectroscopic Instrument, operating from atop Kitt Peak in Arizona, has collected evidence suggesting that dark energy might not be constant at all. Instead, it appears to be changing over time in ways that could fundamentally reshape our understanding of physics and the fate of the universe itself. The implications of this discovery are staggering. If dark energy is indeed evolving rather than remaining fixed, it would represent the first major revision to our cosmological models in over a century. The standard model of cosmology, known as Lambda Cold Dark Matter, has been remarkably successful at explaining the universe we observe. Lambda, in this context, refers to the cosmological constant, a term that Albert Einstein first introduced into his equations of general relativity. This constant was meant to represent a fixed energy density filling all of space uniformly. For 25 years after dark energy was first discovered in 1998, observations seemed to confirm that this simple picture was correct. But now, with unprecedented precision measurements spanning billions of years of cosmic history, we are seeing hints that the universe may be more complex and dynamic than we thought. The story of dark energy begins not with its discovery, but with the realization that the universe is expanding. In 1929, astronomer Edwin Hubble observed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This observation confirmed earlier theoretical work by Alexander Friedmann and Georges Lemaitre, who had proposed that the universe was not static, but dynamically evolving. For most of the 20th century, cosmologists assumed that this expansion would gradually slow down due to the gravitational pull of all the matter in the universe. Some thought the expansion might eventually reverse, leading to a big crunch, where the universe would collapse back in on itself. Others believed the expansion would continue forever, but at an ever-decreasing rate. Then, in 1998, 2 independent teams of astronomers made a discovery that shocked the scientific community. The Supernova Cosmology Project and the High Z Supernova Search Team were studying distant exploding stars called Type Ia supernovae. These stellar explosions are remarkably uniform in their brightness, making them excellent cosmic yardsticks for measuring distances across the universe. By comparing the brightness of nearby supernovae with those billions of light years away, the teams could determine how fast the universe was expanding at different points in its history. What they found was completely unexpected. Instead of slowing down, the expansion of the universe was accelerating. Distant galaxies were flying apart faster and faster as time went on. This discovery was so surprising that the teams spent years checking and rechecking their data, looking for any possible errors. But the result held up. The universe's expansion was definitely accelerating, driven by some unknown force that seemed to act as a kind of anti-gravity, pushing everything apart. The scientists called this mysterious force dark energy, though the name doesn't really tell us what it is. The discovery was so revolutionary that it earned the Nobel Prize in Physics in 2011 for Saul Perlmutter, Brian Schmidt, and Adam Rees, the leaders of the 2 teams. At first, the simplest explanation seemed to be Einstein's cosmological constant. When Einstein developed his general theory of relativity in 1915, he included a term in his equations that represented a constant energy density permeating all of space. He originally added this term to make his equations predict a static universe, which was the prevailing belief at the time. When Hubble discovered that the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his theory. But with the discovery of accelerating expansion, the cosmological constant made a comeback. If space itself has a constant energy density, and if this energy has negative pressure, it would push galaxies apart with a force that grows stronger as the universe expands. This would explain the accelerating expansion perfectly. For the next 25 years, observations continued to refine our understanding of dark energy, and everything seemed to fit with the cosmological constant picture. Studies of the cosmic microwave background, the faint afterglow of the Big Bang, confirmed the basic parameters. Surveys mapping millions of galaxies across cosmic history showed patterns consistent with a constant dark energy. Even gravitational lensing observations, which measure how dark energy affects the growth of cosmic structures, seemed to support the simple model. The cosmological constant became the standard assumption in cosmology, incorporated into the Lambda Cold Dark Matter model that describes the composition and evolution of the universe. But there was always something unsatisfying about the cosmological constant. For one thing, when physicists tried to calculate what the energy density of empty space should be based on quantum field theory, they got an answer that was wrong by a factor of 10 to the power of 120. This is arguably the worst theoretical prediction in the history of science. The value we observe is so much smaller than what we calculate that it suggests we're missing something fundamental in our understanding. Additionally, there's what's called the coincidence problem. If dark energy is truly constant, why does its density happen to be comparable to the density of matter at precisely this epoch in cosmic history? Throughout most of the universe's past, either matter or radiation dominated. In the far future, dark energy will dominate completely. We just happen to live at the special time when they're roughly balanced. These puzzles led some physicists to propose alternative explanations for dark energy. One of the most developed ideas is called quintessence. The name comes from ancient Greek philosophy, where philosophers believed everything was made of 4 elements: earth, water, air, and fire. They proposed a 5th element, the quintessence, that made up the celestial realm. In modern cosmology, we have 4 known types of energy in the universe: ordinary matter, radiation or photons, dark matter, and neutrinos. Quintessence would be a 5th type of energy. Unlike the cosmological constant, quintessence is dynamic. It's envisioned as a field permeating space, similar to how magnetic fields permeate the region around a magnet, but extending throughout the entire universe. This field would have energy, and that energy would create the negative pressure needed to drive cosmic acceleration. The key difference from the cosmological constant is that quintessence can change over time. The strength of the field and its energy density can evolve as the universe expands and ages. In many quintessence models, the field has what's called tracker behavior. Early in the universe's history, the quintessence energy density tracks the radiation density, staying comparable to it. Later, it tracks the matter density. Only recently, in the last few billion years, has quintessence begun to dominate and drive acceleration. This tracker behavior naturally explains the coincidence problem. We don't live at a special time by accident. Instead, the quintessence field is designed to start dominating around now because of its fundamental properties. Various models of quintessence have been proposed, with different forms for the field's potential energy. Some are inspired by particle physics theories, like supersymmetry. Others are purely phenomenological, designed to fit observations without necessarily having a deep theoretical motivation. For 2 decades after dark energy's discovery, observations weren't precise enough to distinguish between these possibilities. The data was consistent with a cosmological constant, but it also couldn't rule out slowly varying quintessence. That started to change with the Dark Energy Spectroscopic Instrument, or DESI for short. This remarkable machine began operations in 2021 atop the Kitt Peak National Observatory near Tucson, Arizona. DESI uses a 4-meter telescope equipped with 5,000 small robotic positioners, each capable of pointing a fiber optic cable at a different galaxy or quasar in the night sky. Every 20 minutes, these robots reposition themselves to observe 5,000 new objects simultaneously. Over the course of its 5-year survey, DESI aims to measure the spectra of more than 40 million galaxies and quasars, creating the most detailed 3-dimensional map of the universe ever made. The way DESI searches for dark energy is elegant and indirect. In the first moments after the Big Bang, the universe was filled with a hot, dense plasma of particles. Sound waves rippled through this plasma, much like sound waves traveling through air. These primordial sound waves left an imprint on the distribution of matter in the universe. Even today, billions of years later, galaxies are slightly more likely to be found at certain distances from each other. This pattern is called baryon acoustic oscillations. The characteristic scale of this pattern acts as a cosmic ruler. By measuring how large this ruler appears at different distances and different times in cosmic history, we can determine how fast the universe was expanding at each epoch. Dark energy affects this expansion rate. If dark energy is constant, the expansion history follows a specific pattern. If dark energy is evolving, the pattern changes in predictable ways. The challenge is that these differences are subtle. You need extremely precise measurements across a wide range of cosmic time to detect them. This is exactly what DESI provides. By observing galaxies at many different distances, corresponding to different look-back times into the past, DESI can trace how the expansion rate has changed over the last 11 billion years. In April of 2024, the DESI collaboration released their first-year results. The data showed something intriguing. When analyzed in isolation, the DESI measurements were consistent with a cosmological constant. But when combined with other observations, particularly data from the cosmic microwave background and type Ia supernovae, there were hints of something more. The combined datasets seemed to slightly prefer models where dark energy evolved over time, rather than remaining constant. The statistical significance wasn't overwhelming, but it was strong enough to generate excitement in the cosmology community. Many scientists expected these hints to fade as more data accumulated. Often in science, early anomalies disappear when you gather more statistics and better understand your systematic errors. But with DESI, the opposite happened. In March of 2025, the collaboration released results incorporating 3 years of observations. The dataset now included measurements from nearly 15 million galaxies and quasars. The evidence for evolving dark energy had gotten stronger, not weaker. The significance level rose from about 3.5 sigma to 4.2 sigma when DESI data was combined with other cosmological measurements. To understand what this means, we need to talk about statistical significance. In particle physics and cosmology, scientists use the Greek letter sigma to denote how unlikely a result would be if it were just a random fluctuation. A 3 sigma result means there's about a 1 in 370 chance of seeing such a result by accident. 4 sigma corresponds to roughly 1 in 15,000. The gold standard in physics is 5 sigma, which means only 1 in 3.5 million chance of a random fluctuation. The DESI results haven't reached that threshold yet, but they're approaching it. What makes the DESI findings particularly compelling is that they're seeing the same trend across different types of measurements and different redshift ranges. Redshift is the astronomical term for how much light from a distant object has been stretched by the expansion of the universe. Higher redshift means looking farther back in time. DESI measures galaxies at redshifts ranging from nearly 0, which corresponds to the present day, all the way up to redshift of about 4, which corresponds to seeing the universe as it was about 12 billion years ago, when it was only about 10% of its current age. The pattern DESI sees is that the equation of state of dark energy, denoted by the letter W, seems to change with redshift. The equation of state is a number that describes the relationship between an energy density and its pressure. For a cosmological constant, W equals -1 exactly. This value never changes. For dynamical dark energy, W can vary. What DESI finds is that W may have been slightly different in the past than it is today. The data suggests that dark energy's repulsive effect may have been stronger in the earlier universe and has weakened somewhat over cosmic history. This might sound counterintuitive. After all, we know the expansion of the universe is accelerating. If dark energy is weakening, shouldn't the acceleration be slowing down? The key is to understand that even a weakening dark energy can still cause acceleration. As long as W is more negative than about -1/3, dark energy will push things apart faster than gravity can pull them together. The DESI data suggests W might currently be around -0.9 or -0.95, somewhat less negative than the cosmological constant value of -1. But this is still more than enough to drive acceleration. Other observations support the DESI findings. The Dark Energy Survey, which operated from 2013 to 2019 using a telescope in Chile, has also analyzed their data and found similar hints of evolving dark energy. Their techniques are complementary to DESI's. While DESI primarily uses baryon acoustic oscillations, the Dark Energy Survey uses multiple methods, including weak gravitational lensing, which measures how the gravity of foreground matter distorts the images of background galaxies. The fact that independent experiments using different techniques are seeing similar signals makes the evidence more credible. The Euclid satellite, launched by the European Space Agency in 2023, is also contributing to this story. Euclid is mapping the three-dimensional distribution of galaxies with exquisite precision, creating the most detailed picture yet of the large-scale structure of the universe. Its first cosmological results are expected in 2026. The Nancy Grace Roman Space Telescope, scheduled for launch by NASA in 2027, will add even more data. Together with the Vera Rubin Observatory, which released its first images in 2025 and will conduct an unprecedented survey of the entire visible sky repeatedly for 10 years. These instruments will either confirm or refute the DESI hints over the next few years. If the evidence continues to strengthen and dark energy is indeed evolving, what would that mean? First, and most obviously, it would mean our standard cosmological model needs revision. The lambda in Lambda Cold Dark Matter would need to be replaced with something more complex. This wouldn't invalidate all our previous work. The standard model would still be an excellent approximation, just as Newtonian gravity remains an excellent approximation, even though we now know general relativity is more accurate. But it would signal that we're missing something important in our fundamental understanding. Second, it would provide our first real clue about what dark energy actually is. A cosmological constant doesn't have much physics behind it. It's just a number you plug into Einstein's equations. But dynamical dark energy requires a physical mechanism. It needs to be something, some field or substance or property of space, that changes over time according to physical laws. This would give theoretical physicists something concrete to work with. They could start building and testing models based on particle physics or quantum field theory or string theory. Quintessence remains the leading candidate for dynamical dark energy. Within the broad category of quintessence, there are many specific models. Some are called thawing models, where the quintessence field was essentially frozen in the early universe and only recently began to evolve. Others are called freezing or tracking models, where the field evolved actively in the early universe and is now settling down toward a nearly constant value. The DESI data, when compared with different quintessence models, seems to prefer scenarios where the field's behavior has changed relatively recently in cosmic history. There's also the possibility of phantom dark energy, a more exotic variant where the equation of state W is less than -1. This would mean dark energy is becoming stronger over time, rather than weaker. Phantom energy has unusual properties. If it dominated the universe's energy budget and continued to strengthen indefinitely, it would eventually tear apart all bound structures. Galaxies would be ripped apart, then solar systems, then planets, and eventually atoms themselves, in a cataclysmic event called the Big Rip. The current data doesn't strongly support phantom energy, but it's not completely ruled out either. Another intriguing possibility is that dark energy is connected to dark matter in some way. Most current theories treat these as completely separate phenomena. Dark matter is the invisible substance that provides the extra gravity needed to hold galaxies together. Dark energy is the repulsive force accelerating cosmic expansion. But maybe they're two aspects of some deeper physics. Some models propose interactions between dark matter and dark energy, where energy can flow back and forth between them. Others suggest that dark energy might be produced by the decay of dark matter particles. These ideas are speculative, but they offer explanations for why dark matter and dark energy have comparable densities at the present epoch. There's even the possibility that dark energy isn't a substance at all, but rather a sign that our theory of gravity needs modification. Einstein's general relativity has passed every experimental test we've given it with flying colors. But perhaps at the largest scales, encompassing the entire observable universe, gravity behaves differently than general relativity predicts. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy. Instead, they change how gravity works at cosmological distances. Most modified gravity theories make predictions that differ from dark energy models in subtle ways that upcoming observations should be able to test. The implications extend to the ultimate fate of the universe. If dark energy is a true cosmological constant, the universe will expand forever at an accelerating rate. Eventually, in the far future, all galaxies beyond our local group will recede beyond our cosmic horizon. The observable universe will shrink to just the merged remnant of the Milky Way and Andromeda galaxies, floating alone in an ever-enlarging void. Stars will eventually burn out, black holes will evaporate through Hawking radiation, and the universe will fade into a cold, dark, dilute state of maximum entropy. This scenario is sometimes called the Big Freeze or heat death. But if dark energy is evolving, other fates become possible. If dark energy continues to weaken as the DESI data hints it might. The acceleration of expansion could eventually slow or even stop. The universe might reach a maximum size and then coast, or it might even begin to contract in a reverse of the Big Bang. This could lead to a big crunch, where all matter and energy eventually collapse back into a singularity. Alternatively, if dark energy strengthens over time, acceleration could increase until reaching the Big Rip scenario. The fate of every atom and particle in existence depends on the behavior of dark energy over timescales of trillions of years. It's worth emphasizing that despite the exciting hints, we're not yet certain that dark energy is evolving. The 4.2 sigma significance sounds impressive, but it's not quite at the 5 sigma level that physicists typically require before claiming a discovery. There are also potential sources of systematic error that could affect the results. For example, the supernova data that's combined with DESI measurements has some uncertainties related to how supernovae evolve and how dust in distant galaxies affects their brightness. The cosmic microwave background data relies on complex modeling of how photons interacted with matter in the early universe. The DESI collaboration is well aware of these challenges and is working carefully to understand all possible sources of error. They've implemented sophisticated blinding procedures to avoid confirmation bias. In a blinded analysis, researchers analyze their data without knowing the final cosmological implications until all the analysis steps are complete. This prevents them from unconsciously tweaking their analysis to favor a particular outcome. The fact that the dynamical dark energy signal has persisted and strengthened through multiple years of increasingly rigorous analysis suggests it's probably real, but absolute certainty will require additional years of data and independent confirmation from other experiments. The community response has been one of cautious excitement. At conferences and in published papers, cosmologists are carefully examining the DESI results from every angle. Some are developing new theoretical models to explain the observations. Others are proposing new tests that could distinguish between different explanations. There's a palpable sense that we might be on the verge of a major paradigm shift in our understanding of the universe. Looking deeper into the technical details, the equation of state parameter W that DESI measures is defined as the ratio of dark energy's pressure to its energy density. For normal matter made of atoms, this ratio is essentially 0. Matter has energy density due to its mass, but negligible pressure. Radiation, like light, has W equal to 1/3. Dark energy, to drive accelerated expansion, must have negative pressure. The cosmological constant has W exactly equal to -1. Values between -1 and 0 would represent dark energy that's less repulsive than a cosmological constant. Values less than -1 represent phantom energy that's more repulsive. The DESI data suggest W might vary with redshift, following approximately what's called a Chevalier-Pulaski-Linde parametrization. This is a simple mathematical form where W depends on redshift through 2 parameters, usually called W0 and WA. W0 represents the current value of W, while WA describes how much W has changed over cosmic history. A cosmological constant would have W0 equal to -1 and WA equal to 0. The DESI data, when combined with other observations, suggests W0 might be slightly greater than -1, perhaps around -0.9, and WA might be negative, indicating that W was more negative in the past. These numbers might seem like splitting hairs, but they're profoundly important. The difference between W equal to -1 and W equal to -0.9 might not sound like much, but it represents fundamentally different physics. It's the difference between a static property of space and a dynamic field governed by physical laws. It's the difference between a mystery we might never solve and a phenomenon we can potentially understand through deeper theories. The baryon acoustic oscillation measurements that DESI uses are based on precise statistical analysis of how galaxies cluster. The primordial sound waves in the early universe created a preferred scale of about 490 million light-years. Galaxies today are slightly more likely to be separated by this distance than by slightly smaller or larger distances. This creates a small bump in what's called the galaxy correlation function, which measures how the probability of finding a galaxy at a given distance relates to the average density. The position and shape of this bump depends on the expansion history of the universe. To extract cosmological information from galaxy clustering, DESI scientists must carefully account for many astrophysical effects. Galaxy formation is influenced by dark matter, gas dynamics, supernova feedback, black hole growth, and many other processes. These create small-scale clustering patterns that must be separated from the large-scale patterns produced by dark energy. The DESI team uses sophisticated theoretical models and computer simulations to understand these effects and ensure they're not contaminating the dark energy measurement. Another complication is that we observe galaxies in redshift space rather than real space. Redshift tells us a galaxy's line-of-sight velocity, which includes both the cosmic expansion and the galaxy's peculiar motion due to local gravitational effects. This creates distortions in how we perceive galaxy clustering. However, these distortions themselves contain cosmological information. They depend on the growth rate of structure in the universe, which is affected by dark energy. DESI's analysis accounts for these effects, extracting both the baryon acoustic oscillation signal and the redshift space distortion signal to constrain dark energy. The cosmic microwave background provides complementary information. This radiation was emitted when the universe was only 380,000 years old, before the first stars formed. Tiny temperature variations in this radiation, about 1 part in 100,000, reflect density variations in the early universe that eventually grew into galaxies and galaxy clusters. The detailed pattern of these variations depends on the universe's composition and geometry. Measurements from satellites like the Planck mission have mapped these variations across the entire sky with exquisite precision. Dark energy affects the cosmic microwave background in subtle ways. It influences how the universe expanded between the time the radiation was emitted and when we observe it today. This affects how the radiation is redshifted and how gravitational lensing by foreground matter distorts its patterns. By combining cosmic microwave background measurements with galaxy surveys like DESI, cosmologists can constrain dark energy much more tightly than either dataset could alone. The cosmic microwave background anchors the early universe, while DESI traces the late-time evolution. Type 1 supernovae provide yet another independent probe. These exploding stars are thought to occur when white dwarf stars in binary systems accrete matter from their companions until they exceed a critical mass, about 1.4 times the mass of our Sun. The explosion is remarkably uniform because it always happens at the same mass. This makes the peak brightness predictable. By comparing the observed brightness to the predicted brightness, astronomers can determine the distance to the supernova. Measuring supernova at different redshifts creates a distance ladder that traces cosmic expansion. The original discovery of dark energy came from noticing that distant supernovae were dimmer than expected, indicating they were farther away than a decelerating universe would predict. Modern supernova surveys have observed thousands of these explosions across cosmic history. The precise shape of the distance-redshift relation constrains dark energy. If dark energy is evolving, the the relation should deviate from the pattern expected for a cosmological constant in specific ways. Recent years have seen intensive efforts to improve supernova measurements. Scientists have worked to better understand the physics of the explosions, the effects of dust in the host galaxies, and how supernova properties might have evolved over cosmic time. Some of these systematic effects could, in principle, mimic the signal of evolving dark energy. This is why independent confirmation from methods like baryon acoustic oscillations is so important. The fact that different techniques are seeing similar hints of evolution makes the case stronger. Looking ahead, the next few years will be crucial for understanding dark energy. DESI will continue observing through 2026, ultimately measuring over 40 million galaxies and quasars. The statistical power of the full dataset will be substantially greater than what we have now. The Vera Rubin Observatory will discover millions of supernovae over its 10-year survey, dramatically improving the supernova distance ladder. The Euclid satellite will map gravitational lensing across billions of galaxies, providing another independent constraint on dark energy. The Nancy Grace Roman Space Telescope will conduct complementary surveys with even higher resolution. By the end of this decade, we should have a much clearer picture. If multiple independent experiments all confirm that dark energy is evolving, it will mark a watershed moment in cosmology. The field will pivot toward building and testing detailed models of quintessence, or whatever the true nature of dark energy turns out to be. If instead the hints fade, and a cosmological constant remains the best fit to all data, we'll have learned that the universe is simpler than recent observations suggested, though the fundamental mystery of why the cosmological constant has its observed value will remain. Regardless of the outcome, the search for understanding dark energy represents science at its best. We're using the most advanced instruments and sophisticated theoretical frameworks to probe the deepest questions about existence. What is the universe made of? How did it begin? How will it end? What are the fundamental laws that govern reality? Dark energy holds clues to all these questions. Its discovery 2.5 decades ago revealed that we didn't understand the universe nearly as well as we thought. The possibility that it's evolving reminds us that nature always has more surprises in store. The human element of this research is worth reflecting on. Thousands of scientists from dozens of countries have collaborated to build instruments like DESI, to collect and analyze data, to develop theoretical models. Graduate students spend years learning the techniques needed to extract cosmological signals from noisy data. Senior researchers devote their careers to understanding the universe's composition and evolution. This collective effort represents one of humanity's most ambitious intellectual endeavors. We're using technology and mathematics to comprehend the cosmos across billions of light years and billions of years of time. There's something profound about the fact that creatures evolved on one small planet, in one ordinary galaxy among hundreds of billions, can figure out that the universe is filled with a mysterious energy that will determine the fate of everything that exists. We've gone from ancient myths about the sky to precise measurements of cosmic acceleration in just a few thousand years of civilization. The current hints about evolving dark energy are part of this long story of discovery, where each answer reveals new questions, and each observation refines our picture of reality. For now, as we await the data that will resolve the question of whether dark energy truly evolves, we are left in a state of productive uncertainty. This is actually an exciting place to be in science. We have genuine puzzles that push the boundaries of our understanding. We have tools capable of solving these puzzles. We have creative minds developing new ideas and testing them against observation. This is exactly how progress happens. whether dark energy turns out to be a cosmological constant, quintessence, or something else entirely. The process of finding out will teach us things we didn't even know to ask. The implications ripple far beyond cosmology. If dark energy is a dynamic field, it might connect to other areas of physics. Perhaps it's related to the Higgs field that gives particles mass. Perhaps it emerges from the structure of space-time itself at quantum scales. Perhaps it's a window into physics beyond the standard model of particle physics. Understanding dark energy could help resolve other puzzles, like why the cosmological constant problem exists, or how to reconcile quantum mechanics with gravity. It's also worth considering what these discoveries mean for our place in the universe. The realization that ordinary matter, the stuff we're made of, comprises less than 5% of the universe's total energy was humbling. Dark matter and dark energy dominate, and we understand neither. But this ignorance is empowering in its own way. It means there's so much left to discover. The universe is stranger and more wonderful than we imagined. Every time we think we've figured it out, nature shows us something new. The measurement techniques used by DESI represent the culmination of decades of development in astronomical instrumentation and data analysis. Each of the 5,000 robotic fiber positioners in the DESI instrument can move independently to point at a specific target in the sky. The robots use small motors to adjust the position of fiber optic cables that carry light from distant galaxies into a sophisticated spectrograph. This spectrograph splits the light into its component wavelengths, creating a spectrum that reveals the galaxy's chemical composition and redshift. The entire process, from positioning the fibers to recording spectra, takes about 20 minutes per observation. Then the robots reposition for the next 5,000 targets. The precision required for these measurements is remarkable. To detect the subtle signature of baryon acoustic oscillations, DESI must measure galaxy positions to better than 1% accuracy across billions of light-years. Redshifts must be measured precisely enough to distinguish between galaxies separated by just a few million light-years. This requires not only excellent hardware, but also sophisticated software to process the enormous amounts of data. Every night of observation produces terabytes of information. Over the course of the 5-year survey, DESI will generate hundreds of terabytes of spectra that must be carefully calibrated, analyzed, and interpreted. The statistical methods used to extract cosmological information from this data are equally sophisticated. Scientists use techniques from Bayesian statistics to properly account for all sources of uncertainty. They perform extensive tests on simulated data to ensure their analysis methods are working correctly. They compare results from different subsets of the data to check for consistency. They even use blinding techniques, where certain parameters are hidden during the analysis to prevent unconscious bias. This level of rigor is necessary because the signals they're looking for are subtle, and the implications are profound. The connection between dark energy and the fundamental constants of nature is another fascinating aspect of this research. Some theoretical models predict that if dark energy is a dynamical field, it might cause other fundamental constants to vary slowly over cosmic time. For example, the fine structure constant, which governs the strength of electromagnetic interactions, or the ratio of the proton mass to the electron mass, might change imperceptibly as the dark energy field evolves. Astronomers have searched for such variations by observing the spectra of distant quasars, looking for tiny shifts in the wavelengths of spectral lines that would indicate the constants were different billions of years ago. So far, these searches have found no convincing evidence of variation, placing tight constraints on how strongly dark energy can couple to ordinary matter. The quantum field theory perspective on dark energy adds another layer of complexity. In quantum field theory, even empty space is never truly empty. The vacuum seethes with quantum fluctuations, virtual particles constantly popping into and out of existence. These fluctuations contribute to the energy density of the vacuum. In principle, every field in nature, from the electromagnetic field to the Higgs field to fields we haven't discovered yet, adds to the vacuum energy. When physicists try to calculate the total vacuum energy by adding up all these contributions, they get a result that's absurdly large. This is the cosmological constant problem, and it's one of the deepest puzzles in theoretical physics. Various solutions to the cosmological constant problem have been proposed over the years. Some invoke a symmetry called supersymmetry, which would cause contributions from different types of particles to cancel out. But supersymmetry, if it exists, must be broken at energies we can reach with current particle accelerators. And this breaking itself would generate vacuum energy. Others suggest that maybe our universe is just one of countless universes in a vast multiverse, and we happen to live in one of the rare universes where the vacuum energy is small enough for galaxies and stars to form. This anthropic explanation is philosophically troubling to many physicists, because it seems to abandon the search for a fundamental explanation. Quintessence models offer a different approach. Rather than trying to explain why the cosmological constant is small, they replace it with a dynamical field whose energy density naturally evolves to a small value in the present epoch. The field starts with some initial energy in the early universe, but as space expands, the field rolls down its potential energy landscape, like a ball rolling down a hill. The shape of this potential determines how the field evolves. If the potential is flat enough, the field rolls slowly, and its energy density remains comparable to the matter density throughout cosmic history. This tracker behavior means the field naturally comes to dominate around the present epoch without requiring fine-tuned initial conditions. Different forms of potential energy functions lead to different predictions for how dark energy evolves. Exponential potentials, power law potentials, and inverse power law potentials have all been studied extensively. Each has different mathematical properties and different observational signatures. Some potentials are motivated by fundamental physics theories, like string theory or supergravity. Others are more phenomenological, designed to fit observations without necessarily having a deep theoretical foundation. The DESI data, if it continues to show evidence for evolving dark energy, will help narrow down which types of potentials are consistent with reality. The interplay between observation and theory in cosmology is a beautiful example of how science progresses. Theorists propose models based on mathematical consistency and physical intuition. Observers design experiments to test these models. When observations agree with predictions, our confidence in the models grows. When observations reveal surprises, theorists go back to their equations to develop new ideas. This iterative process has driven cosmology from a speculative philosophical discipline to a precision science over the past century. The role of computer simulations in modern cosmology cannot be overstated. To predict what the universe should look like under different dark energy models, scientists run massive computer simulations that follow the evolution of billions of particles under the influence of gravity. These simulations start with initial conditions matching what we observe in the cosmic microwave background and evolve forward in time to the present day. By comparing the distribution of matter in simulations to what we observe in galaxy surveys, cosmologists can test whether our theories are correct. Incorporating dark energy into these simulations adds complexity, because dark energy affects not just the expansion rate, but also how structures grow over time. The Dark Energy Survey, which ran from 2013 to 2019, used multiple techniques beyond baryon acoustic oscillations to constrain dark energy. Galaxy cluster counts, which measure how many massive clusters of galaxies exist at different epochs, are sensitive to dark energy because dark energy suppresses the growth of structure. Weak gravitational lensing, which measures how foreground mass distorts images of background galaxies, traces the total matter distribution, including dark matter, and can detect the effects of dark energy on structure growth. Type Ia supernovae provide direct distance measurements. Combining all these probes provides robust constraints that don't depend on any single measurement technique. The systematic uncertainties in each of these measurements must be carefully quantified. For supernova measurements, uncertainties arise from dust extinction in the host galaxies, from the possibility that supernova properties have evolved over cosmic time, and from the details of how supernova brightness is standardized. For weak lensing, uncertainties come from intrinsic alignments of galaxies, from the effects of baryonic physics on the matter distribution, and from the accuracy of photometric redshift estimates. For galaxy clustering, uncertainties arise from galaxy bias, the relationship between the distribution of visible galaxies and the underlying dark matter distribution, and from redshift space distortions caused by galaxy peculiar velocities. Each systematic effect must be modeled, measured, and accounted for in the final analysis. This is painstaking work, requiring careful attention to detail and extensive validation. The DESI collaboration has published dozens of papers describing their systematic error analysis, demonstrating that they've considered every possible source of contamination. This thoroughness is essential because the signals they're looking for are subtle. A systematic error of just 1 or 2% could mimic or mask the signature of evolving dark energy. The international nature of this research reflects how cosmology has become a global enterprise. DESI includes researchers from the United States, Canada, Mexico, the United Kingdom, France, Spain, Switzerland, Germany, Italy, and China, among other countries. The Euclid mission involves scientists from across Europe and the United States. The Vera Rubin Observatory is funded by the United States, but will provide data to scientists worldwide. This collaboration across borders and institutions brings together diverse perspectives and expertise. It also means that the discoveries made by these experiments belong to all of humanity, not just to any one nation or institution. The philosophical implications of dark energy research extend beyond the immediate scientific questions. Understanding dark energy means understanding the ultimate fate of everything that exists. Will the stars continue to shine until their fuel is exhausted? Or will they be torn apart by ever-strengthening dark energy in a big rip? Will galaxies drift apart until each becomes isolated in an expanding void? Or will the universe eventually contract in a big crunch? These questions touch on deep issues about the nature of time, causality, and existence itself. Some physicists have speculated about even more exotic possibilities. What if dark energy is not uniform, but has spatial variations? What if it interacts with dark matter in unexpected ways? What if it's connected to extra dimensions of space that we can't directly perceive? String theory, which attempts to unify all the forces of nature, including gravity, predicts the existence of additional dimensions beyond the 3 of space and 1 of time that we experience. These extra dimensions might be curled up at tiny scales, but they could still influence dark energy through subtle quantum effects. The landscape of string theory, a vast space of possible vacuum states, has been invoked to explain why the cosmological constant has its observed value. In this picture, there are countless different vacuum states, each with different values of the cosmological constant and different physical constants. Our universe happens to occupy one particular state where the cosmological constant is small enough for structure to form. This anthropic explanation is controversial because it seems to give up on finding a unique prediction for the cosmological constant, but it might be correct. Nature doesn't have to conform to our preferences for how theories should work. Looking even further ahead, future space missions and ground-based experiments will continue pushing the boundaries of dark energy research. The concept for a space-based gravitational wave detector could detect how dark energy affects the propagation of gravitational waves across cosmic distances. Surveys of neutral hydrogen gas using radio telescopes could map the matter distribution in the universe at high redshift, tracing the transition from matter domination to dark energy domination. Advanced gravitational lensing surveys using extremely large ground-based telescopes could measure the growth of structure with unprecedented precision. The timeline for answering the question of whether dark energy evolves extends over the next decade. By the early 2030s, we should have accumulated enough data from multiple independent experiments to reach a definitive conclusion. If the evidence continues to mount in favor of dynamical dark energy, it will mark the beginning of a new era in cosmology. Theorists will have their work cut out for them, developing and testing detailed models. Observers will design new experiments to measure the properties of dark energy with ever greater precision. The field will be energized by the realization that we're on the cusp of understanding one of the universe's deepest mysteries. The story of dark energy is still being written. The next chapters will unfold over the coming years as more data accumulates. Scientists will continue refining measurements, developing theories, and testing predictions. Perhaps by the end of this decade, we'll look back on the 2025 DESI results as the moment when our understanding of dark energy began to shift. Or perhaps those hints will prove to be statistical fluctuations or systematic effects. Either way, we'll have learned something valuable about how the universe works. That pursuit of knowledge, that willingness to question our assumptions and follow the evidence wherever it leads, is what makes this such an exciting time to be exploring the cosmos.